Okay, looking at section 4.6, page 8. A particle moves along the parabola y equals x squared in the first quadrant in such a way that its x-coordinate in meters increases at a constant rate of 10 meters per second. How fast is the angle of inclination, theta, of the line joining the particle to the origin changing when x is 3? Oh my goodness. A particle moves along the parabola y equals x squared in the first quadrant in such a way that its x-coordinate in meters increases at a constant rate of 10 meters per second. How fast is the angle of inclination of the line joining the particle to the origin changing when x is 3? So we need to sketch a graph. Y equals x squared. Okay, in the first quadrant, so we don't need this part over here, but that's all right. If we have it, no big deal. In the first quadrant, its x-coordinate increases at a constant rate of 10 meters per second. So first off, let's choose some arbitrary point up here, right here. Call it x, y. And to generate that point, we know that we had to go horizontally x and vertically y. So this distance here is x, and that distance there is y. And we want to find how fast is the angle of inclination, that's the angle, joining the particle to the origin. Now there's your particle, let's call it P for particle. Joining that particle with the origin, there's that line joining the particle with the origin. Here's theta, that angle right there. All right, what do we know? And what is it that we want to find? We know that x-coordinate is changing at a rate of 10, so dx dt is 10 meters per second. And we want to find d theta dt when x equals 3. Once we have this information, we need to write an equation that relates x and theta. X and theta. We're going to have to use some trig here. How about tangent? Tangent of theta would be opposite side over the adjacent side, so that would be y over x. But then when we look at this equation, we have too many variables. We have a d theta, that matches, a dx dt, that matches, but no dy dt's in here. So we need to replace out that y. And we can replace that y with x squared because y is equal to x squared. So we'll have tangent theta is x squared over x, or tangent theta is just x. Now let's do a derivative. The derivative of tangent, secant squared theta, d theta dt, equals the derivative of an x is dx dt. And then let's plug in the information that we know. We know dx dt is 10, so that 10 is going in here. Secant squared theta d theta dt. Solve for d theta dt, and we'll have 10 over secant squared theta. All right, now we have to evaluate d theta dt when x is 3. And we have 10 over secant squared theta. Uh-oh, there's nowhere at all to plug in and x equals 3. What we're going to have to do, as we do always, is go back to this original relationship, original diagram. It's easier to go off of this diagram. X is 3, so that's going to be here. Theta is here. And we know this because this graph is on y equals x squared. So if x is 3, this piece has to be 9. All right, now you can use the calculator and inverse trigs to figure out what theta is, and then go back in and figure out what secant is. But it might be easier just to think about this triangle right here. You can find that hypotenuse from 3 squared plus 9 squared is that hypotenuse squared. 9 plus 81. H is going to be the square root of 90, or 3 square root 10. Now we see cosine theta is adjacent over hypotenuse 3 over 3 square root 10. But we want secant. So secant is just the square root of 10. Now we can plug that in right down here. Secant squared theta. Well, secant is square root of 10, so this is square root 10 squared. And d theta dt when x is 3 is 1. All that work for a 1. All right, last little bit here. Units. What are our units in? This is rate of change of an angle. Angles in calculus are always measured in radians, so that angle is increasing at a rate of 1 radian per second. When x is 3. Perfect. Thank you very much. Please tune in for page 9.